It's my great pleasure to give this online talk, and the title is Standard versus Non-Standard Quantum Clocks, and this work is based on the collaboration with Xingang and Mohammad Hossein 5 years ago, and also a recent paper with my students Zun and Yuhang. There is no doubt that inflation is the most successful theory of the primordial universe. However, there are also some alternative theories of inflation which also exist on the market. And if we parameterize different theories of the very early universe as scale factor equals to time to some power p, in this parameterization, inflation corresponds to the value of p is greater than 1, usually much greater than 1. And if we also include superinflation, where the universe expands faster than exponential, that corresponds to the value of p is smaller than -1. However, there are some other possibilities. For example, slow expansion or emergent expansion corresponding to p somewhere here, and slow contraction, fast contraction. The example of slow or emergent expansion including string gas cosmology and Galileo genesis, and slow contraction, for example, the ecliptic scenario, and fast contraction, for example, the matter bounce scenario. There are a lot of debates if these alternative of inflation theories are healthy theories or they are sick, they shouldn't be considered, a lot of theoretical debates. But here, we are not getting into the theoretical debates, but we are talking about a more practical point of view. As long as there are these theories on the market, as long as there are these debates, what about let's use observations to settle the debate, using observations to select which theory is the theory of the very early universe. For this purpose, we'd like to search for methods which can model independently tell if the primordial universe comes from inflation or alternative to inflation. Why model independence is so important? Because there are so many models of inflation. So you can find a lot of different predictions of inflation. And there are not so many models of alternatives simply because people are not studying them. Otherwise, there are also a lot of alternative to inflation that we can imagine. So we really want something model independent and rely on the feature of exponential expansion of inflation or some corresponding expansion history in alternative to inflation. So how can we do that? One of the methods, very well known, is through the primordial gravitational waves. If we observe the primordial gravitational waves, we know the energy scale of either inflation or alternative to inflation. And once we find out the energy scale of that scenario, and then we see the tilt of the gravitational wave, we measure the spectrum of gravitational wave for a certain period. In this case, we know the energy of the universe for a certain development of time. And then we know if it is inflation or it is alternative to inflation. So this is a very important way to tell if our primordial universe comes from inflation or comes from alternative. However, it's not perfect. There are some important assumptions in the approach of primordial gravitational wave to test if our universe comes from inflation or alternative. One assumption is that the primordial gravitational wave assumes we are observing the constant mode. So we know a second-order differential equation for the amplitude of the gravitational wave has two solutions. In an expanding universe, constant mode and decaying mode. For sure, we choose the constant mode. However, if we want to tell the primordial universe was expanding or contracting, we cannot make this assumption. And if we are not making this assumption, one finds that matter bounce, that the universe was contracting in a matter-dominated era, also have a scale invariant, nearly scale invariant primordial gravitational wave spectrum. And the assumption 2 is assuming that the fluctuation arises from the vacuum, which is not always the case either. For example, in string gas cosmology, it was assumed that both the density fluctuation and the primordial gravitational waves comes from the holographic thermal fluctuations. And that breaks the assumption, and as a result, the spectrum of the primordial gravitational wave is also almost scale invariant. Not perfectly, it's even slightly blue-tailed, but almost scale invariant. So there are different assumptions, and if you consider different theories fairly, there are theories which can confuse the prediction of inflation. And also, so I'm not criticizing gravitational wave, it's great, but also we don't know what is the amplitude of primordial gravitational waves. It could be pretty large and we see it in the near future, or it could be very small that we don't hope to see it even in any predictable future. So we don't know the amplitude of the primordial gravitational waves, so we had better to have some complementary ways to test if our universe arises from inflation or not inflation. And what are possible different ways to test our expansion or contraction history of the primordial universe? To answer this question, let us go back a little bit to think about the following question. For a decade or two, we were saying that we have entered a precision era of cosmology. But actually, it is a little bit embarrassing if people ask you, you are saying that now we are in a precision era of cosmology, but actually we don't even know that our universe, our early universe is expanding or contracting, all right? Then how can we say that our current cosmology is precise? We don't even know the most fundamental nature. The primordial universe is expanding or contracting. All right, yes or no? In some observables, we are extremely precise, but in some observables, we are not precise at all. For example, in the size of fluctuation, we can measure the size of fluctuation very well. And how to measure the size of fluctuation? We measure at different scales. And these different scales, K, corresponds to a horizon crossing time, which is a conformal time. In other words, the precision measurement is the size of the fluctuation as a function of comoving time. This correspondence is very precise. However, what about the size of the fluctuation as a function of physical time, or the comoving time as a function of physical time? We cannot read off this information from the power spectrum of inflation or even higher order correlations of light fields. So as a result, if we lack of this information, it is difficult to tell if the universe was expanding, contracting, what kind of evolution history. This is because the scale factor is the ratio of differentiation of conformal time and physical time. If we don't know this relation, we don't know the scale factor. This is the difficulty, all right? The physical time is the difficulty. And here is the idea of classical standard clocks. The idea first arises in Xingang's paper that assuming if there is a heavy field, the heavy field for some reason, for example, falls into a potential or any other reason that the heavy field starts to oscillate. What is this oscillation frequency? The frequency is determined by the mass, which is a physical parameter, which is associated with physical time. So once we see the oscillatory signal in the power spectrum, we know a function between the physical time and the comoving time. And then we know the scale factor. This is the idea. And in technical details, the calculation of the power spectrum involves this kind of integral. Here, there is ik tau, which is the oscillation of the light field, and imt, which is the oscillation of the heavy field. So from the light field, we have conformal time. From the heavy field, we have physical time. And this integral usually is cancelled by these fast oscillations unless there is a resonance or there is a saddle point approximation. At the saddle point, the relation between the physical time and the conformal time is imprinted onto the power spectrum such that the correction to the power spectrum is of sine of k of 1 over p power. where this 1 over p is the inverse function of the scale factor, which is t to the pth power. So once this kind of oscillation is seen in the sky in the power spectrum, that indicates that our primordial universe comes from inflation. So this is the classical standard clock. And there are some debates about standard versus non-standard clocks. And the question is, there are so many possibilities in the early universe. For example, if one studies some generalized scenario of inflation, where the kinetic term of the additional field is coupled non-trivially to the inflaton, and also the mass term of the additional field is generated non-trivially from the inflaton. In this case, the oscillatory scenario, by carefully choosing the function dependence of f phi and m phi, can mimic the case of alternative to inflation, for example, a matter contraction. In other words, if we consider complicated enough scenarios that can confuse inflation between alternative to inflation, and that is known as non-standard clocks. Non-standard means tick and tock of the oscillation doesn't correspond to physical time. So it is non-standard clock, but it will have very similar observational consequence if we twin this f and m dependence. This is about the non-standard clock. All right? And previously, standard or non-standard, we were talking about classical clocks. By classical clocks, I mean that the field is oscillating classically. And the classical oscillation can usually give us a large contribution, but we need some luck. Well, it is well motivated. We have a lot of models which can give us these oscillations, but we need some luck for this to happen, and happen at the stage of CMB or large-scale structure, which is observable to us. So we need some luck. And is it possible to consider some sort of oscillation of the heavy field, which is always there, which we don't need luck to realize? And that is true. That is the quantum fluctuation. So if there is a quantum particle, and that quantum particle always carry a phase with the particle, that doesn't need luck, doesn't need the field to be kicked classically. So this is the motivation to study quantum standard clocks, study the quantum phase, quantum oscillation of the particles which are created in the primordial universe. Usually the signal is small, it's more difficult to observe. However, it is more universal. We don't need luck. And the detailed mechanism is as follows. First of all, a heavy particle is produced in the early universe, either inflation or alternative to inflation, and then the associated production of this heavy particle is related to some massless particle, some light particle, for example, the inflaton, which eventually we can observe. And the associated production is dominated by a resonance. Resonance means the K over A of the light particle coincides with the mass of the heavy particle. All right? And after a while, the universe either expands or contracts. Let's assume the universe expands. And then the wavelength of the light and heavy particles, both of them become longer. The wavelength becomes longer. And after a while, the heavy particle decay to some light particle like the inflaton. And then the decay is also dominated by a resonance if there is, and that means the K over A of the light particle coincides with the mass of the heavy particle, the same as the wavelength at here. However, the particle, the light mode here has already expanded to that length. That means when we are trying to find out the signal of the heavy particle, we have to rely on the correlation between long wavelength modes and short wavelength modes, which is non-Gaussianity. Here we are showing 4-point correlation, and 3-point correlation is also pretty similar. So here, by seeing this scenario, we are going to find out the existence of the heavy particle here, which by itself is important as the whole industry of cosmological collider physics. But on the other hand, this can also tell you about the evolution history of the universe. And what is the signature here? The signature just follows from elementary quantum mechanics that the heavy field evolving from here to here, it evolves by some time, so it's changed by a phase. And that phase change is e to the im delta t. That means if we calculate the correlation function will include this im delta t here. And now, if we assume the universe is inflating, then this im delta t factor, the t can be written as logarithm of the scale factor, and the logarithm of the scale factor by the resonance condition, the logarithm of scale factor can be written as k over m. And then it will become the exponential of logarithm of the ratio of k. So this exponential logarithm or sine cosine of logarithm is the characteristic observational consequence of inflation as predicted by the quantum standard clock. And if it was not inflation, but alternative to inflation, you insert the t and scale factor dependence, which is an inverse function, and then similarly, you will get a function dependence where is sine cosine exponential of k, where k is the hard momentum of the 1 over p power, where this 1 over p is the inverse function, again, of the scale factor. And finally, let's arrive at the question, can we have quantum non-standard clock scenarios, which means the oscillatory signal there, for example, is not coming from inflation, it's coming from alternative to inflation, but that can mimic the sine log behavior, which is the characteristic standard clock for inflation. Is it possible? Actually, it is not only possible, but it's pretty general and natural. Why it is the case? This is because there is a very good motivation to study the mass of all the Hubble scale in the primordial universe. For example, the mass of Hubble parameter can be generated by the self-interaction of light fields. It can also be generated by the light fields non-minimally coupled to the Ricci scalar. And also, if there is supersymmetry breaking in the primordial universe, that supersymmetry breaking could also generate some fields with mass of the Hubble parameter, although it's not always the case. For inflation scenarios, we don't have to distinguish this induced mass or the original constant mass, since the Hubble parameter is almost a constant. However, in alternative to inflation scenarios, we have to be careful, since the Hubble parameter for alternative to inflation is strongly time-dependent, and the mass is strongly time-dependent, and then what is the corresponding clock signal? The oscillation as a function of the shape of the correlation function. What's that? The corresponding oscillatory signal is exponential to the IMT, but here mass is a variable, depends on time, so it becomes I integral of m dt. And then, if the mass is proportional to the Hubble parameter, that means up to some constants, that's exponential of h dt, and we know the Hubble parameter is 1 over t up to some constants, up to some constant p. Yeah, sorry, I forgot to add a p here, but that doesn't matter for our general discussion. It will be proportional to some integral of dt over t, which is a logarithm of t. What it means is the sine, cosine exponential of logarithm of t emerges. And that was the characteristic observational consequence of inflation. But now it is generated from alternative to inflation simply because the mass is 1 over time. And then we have calculated the details of the 3-point correlation function of this induced mass in the squeezed limit. And indeed, we have the sine and the logarithm dependence, which is very similar to the case of quantum standard clock of inflation. And here we have a general p, it's not necessarily inflation. Only if p taken to infinity limit, we have inflation. How to interpret this result? Do we mean that we are unable to distinguish inflation and alternative? That's not the case, fortunately. We can still distinguish inflation and alternative to inflation. not from the sine log. This is identical, but the pre-factor in front is different. The pre-factor is the hard momentum k to some power. And here, this power for inflation, including sub-exponential and super-exponential inflation, the power here is always smaller than 0, corresponding to a decreasing signal as a function of the hard momentum. However, for alternative to inflation, where absolute value of p is smaller than 1, this factor here is always positive, corresponding to an increasing signal of the correlation function as a function of the hard momentum. So there is oscillation, the sine log oscillation, and the amplitude could be larger and larger, corresponding to alternative, could be smaller and smaller, corresponding to inflation. This is the conclusion. So finally, to conclude, if in the future a quantum clock signal is seen, because in the future there are so many upcoming experiments, especially for sphere X in the near future and 21 centimeter in the distant future, if a quantum clock signal is seen by any of these experiments, the question that we ask is, do we see a sine log signal, or do we see a sine of k to some 1 over p power with small p? Which do we see? If we see this sine of k to the 1 over p power with small p, that's very simple. We have alternative to inflation, and by measuring the value of p from fitting the scenario, we know what alternative to inflation. What is the value of p in A equals to t to the pth power? Then we know the early universe. And then, if we see the sine log scenario, we have to distinguish the standard clock and non-standard clock, where the mass is generated dynamically, which is proportional to Hubble parameter, which is 1 over t. If we see the 3-point function increases with k, that means we have alternative to inflation. And if we see the 3-point function decreases with the hard momentum k as it oscillates, that means we have inflation. And for sure, this conclusion is up to unknown other non-standard clock scenarios. If you find some other non-standard clock scenarios, this flowchart may become more complicated. All right, thank you.